Hello, in this video we look in general to the first Nobel Prize in Chemistry from 1901. There will be next video dealing with the Nobel Prize lecture given by Jacobus, Henricus van Hoff. And why did he get it? In short, for his discovery of the laws of chemical dynamics and osmotic pressure in solutions. This is from Wikipedia. Here you see his Nobel Prize diploma, by the way. Beautifully decorated. And here you see the official declaration why he got the prize, coming from the official Nobel Prize site. All information in this video comes from that site, by the way. And this is a quote: "At a fundamental level, chemistry deals with how molecules are composed of atoms and how atoms and molecule comes in contact and forms new constellations." At that time, whether molecules and atoms really existed was still in question during that time. During the 1870s and 1880s, Jacobus van Hoff made pioneering contributions with respect to both the structure of molecules and various sequences of events. A theory about osmotic pressure explains how concentrations even out in solutions that are separated by a membrane always the solvents allow to pass through, but not the dissolved substance. For instance, if you have salt water and you have a membrane separating the two sides of a tank, the water can pass through the membrane, but the salt cannot. Other works deal with chemical relations and how temperatures affect them. I said, coming from the official site. Here is the link. There's also a biographical part on that site, and also some quotes are given from that, which seem to me important. As you can see, it's not a complete biographical part, but only a summary. Van Hoff has acquired fame, particularly by epoch-making publications. His doctoral thesis was entitled Bijdrage tot de kennis van cyaanzuren, that's in Dutch, he was Dutch, en malanzuur, which in English is Contribution to the Knowledge of Cyanoacetic Acids and Malonic Acid. Of far greater weight, however, was his publication, which appeared several months before, Voorstel tot uitbreiding van het tegenwoordige in de scheikunde, again, gebruikt de structuurformules in de ruimte, again, this is Dutch. English, Proposal for the Development of Three-Dimensional Chemical Structural Formulas. Until that time only, if a picture was taken of a formula, it was always flat, two-dimensional. He proposed to use three-dimensional molecules represented in space, three-dimensional space instead of two-dimensional. This small pamphlet, consisting of 12 pages text and 1-page diagrams, gave the impetus to the development of stereochemistry, thus chemistry in 3 dimensions. The concept of the asymmetrical carbon atom dealt with in this publication supplied an explanation of the occurrence of numerous isomers, inexplicable means of the then current structural formula. What is an isomer? We come to that later when there is a picture about it. So I park it for now for a moment. At the same time, he pointed out the existence of relationships between octable activity and the presence of asymmetrical carbon atoms. His revolutionary ideas, however, only found acceptance after the publication in 1875 of his Chimie, that's French, it's difficult, Chimie dans l'espace, especially when 2 years later the German translation appeared with an introduction by Licinius. The English translation is Chemistry in Space, and it did not appear until 1891. In his 10 années dans l'histoire d'une théorie, that's 10 years in the history of a theory, he drew attention to the fact that J.A. Nobel had independently arrived at the same ideas too in a more abstract form. Now, go back to the stereochemistry. You see, this is supposed not to be a flat picture, but a three-dimensional picture. So this is in fact a pyramid with 4 triangles. This is called so R1, R3 and R2 are on the ground, and R3 is dus further back. inside. So it's three-dimensional picture, not a flat picture. And here's the fourth point, that's R4. Well, that's just one variety of this 4-carbon atom. You see here is another one. Again, here I have R1, R2, R3, but this time in 3 dimensions. This is further back. But here, this time the R4 atom is not above, but below the others. So you can, these are two different, they have the same structural formula, C4, 4 carbon atoms. This one has 4 carbon atoms and this one too. So until then they were not, could not be separated, but now if you see them as a 3-dimensional, you see that they are different. The ground 3 have the same position in both, but the 4th is above and here below. These are called isomers. Yeah. Okay. In his book Études de dynamique chimique, Study of Dynamic Chemistry, appeared, in which he entered for the first time the field of physical chemistry. Of great importance was his development of the general thermodynamic relationships between the heat of conversion and the displacement of the equilibrium as a result of temperature variation. At a constant volume, the equilibrium in the system will tend to shift in such a direction as to oppose the temperature change, which is imposed upon the system. Thus, lowering the temperature results in the heat development, while increasing the temperature results in heat absorption. It's a sort of inertia. It's a reaction against, in the opposite direction as the influence from the outside. This principle of mobile equilibrium was subsequently in 1885 put in a general form by Le Chatelier, who extended the principle to include compensation by change of volume for imposed pressure changes, and it is now known as the Hoff-Le Chatelier principle. The following year, in 1885, followed l'équilibre chimique dans le système gazeux au-dessous à l'état dilué. French-speaking listeners will probably be disgusted by the pronunciation, but it's not my birth language, neither is English, by the way. In English, it's chemical equilibria in the gaseous system or strongly diluted solutions, which dealt with his theory of dilute solutions. Here he demonstrated that the osmotic pressure in solutions which are sufficiently dilute is proportional to the concentration and the absolute temperature, so that this pressure can be represented by a formula which only deviates from the formula for gas pressure by a coefficient I. We come back to that in the lecture video, the second video. He also determined the value of I by various methods, for example by means of the vapor pressure, and results on the lowering of the freezing point. Thus Van 't Hoff was able to prove that thermodynamic laws are not only valid for gases, this is the important part probably, but also for dilute solutions. So there was an analogy between the two phenomena. As pressure laws given general validity by the electric discharging theory of Arrhenius, who also got the Nobel Prize by the way later, the first foreigner who came to work with him in Amsterdam, considered the most comprehensive and important in the realm of natural sciences. During his Berlin period, he was there from 1896 to 1905, continuously engaged on the problem of the origin of oceanic deposits with special reference to those formed at Strasbourg. In his extensive work he was especially assisted by W. Meyerhofer, who had previously worked with him in Amsterdam for a number of years. He was probably the first to apply small-scale results obtained in the laboratory to phenomena occurring on a larger scale in nature. The results of his ambitious investigation, mostly published in the Proceedings of the Prussian Academy of Science, were summarized by him in 2 volumes work zur Bildung ozeanischer Salzablagerungen, dus the creation of oceanic salt layers, in 1905 to 1909. Van 't Hoff greatly valued the power of imagination in scientific work, as is apparent from his inaugural address on taking up his professorship in Amsterdam. Verbeeldingskracht in de wetenschap, that's again Dutch. In English that is the power of imagination in science, in which he rather elaborately studied biographies. He arrived at the conclusion that the most prominent scientists have possessed this quality in high degree. For instance, William Alsell, also a Nobel Prize winner later, who together with him established de Zeitschrift für physikalische Chemie, dus the magazine for physical chemistry, and can be regarded as founder of the physical chemistry. Here you see them in this picture together. This is Van Hoff and this is Oswald in 1932, this is sometime later. There's also an award ceremony speech for each Nobel Prize. This one is given by C.T. Oetner on Van Hoff, of course. Again, quotes from the official site, there's not the whole ceremony speech, only the parts I think are relevant. With regard to atomic theory, Van Hoff, following an idea put forward by Pasteur, advanced the hypothesis that elementary atoms have attachment points geometrically oriented in space. We saw that with the 4 carbons. A hypothesis which, insofar as carbon compounds are concerned, led to the theory of the asymmetry of carbon atoms and the founding of stereochemistry. Still more revolutionary were Van Hoff's discoveries in the field of molecular theory. Van Hoff's investigations showed that the law, which has been named after the Italian Avogadro, according to which the number of gas molecules in a given volume is the same for all gases at the same pressure and temperature, embraces not only substance in the gaseous phase, but also in solution, provided that the pressures, known as osmotic pressure, is taken into account in the same way as the gas pressure is in the case of gases. There's again an analogy between solutions and gases. It proved that the gas pressure and osmotic pressure are identical, and thereby that the molecules themselves in the gaseous phase and in the solutions are also identical. That's even more important probably. As a result of this, the concept of the molecule in chemistry was found to be definitive and universally valid to a degree hitherto undreamed of. He also discovered how to express the state of chemical equilibrium in reactions and in the electromotive force if a reaction can produce. He explained how the transition occurs between the various modifics. By applying these same simple principles, which were originally borrowed from mechanics and thermodynamics, Van Hoff became one of the founders of chemical dynamics, actions of elements between hydrates or differing water contents, how double cells are formed, etc. His researches have been a substantial factor in bringing about the magnificent advances in physical chemistry, in which field his discovery match the great contributions which other investigators, including those in our country, the Sweden, have made in the field of electrochemistry and in the theory of chemical reaction. This has opened a great prospect for scientific research. On the other hand, the investigations on the state of substances in solutions have had, and will continue to have, the greatest practical consequences. Consequences whose benefit to mankind can best be appreciated if we remember that chemical reactions occur predominantly in solutions, and that the vital functions of living organisms are maintained by metabolic processes which also take place in solutions. Again, this is from a ceremony speech. The complete speech you can find on the official Nobel site. This is the address. And as last, a statue in Rotterdam of Van Hoff. As said, there's also another video coming which will deal more in detail with his lecture. Maybe till